Our topic for today is projectile motion. Now, first of all, let's just define what a projectile is. A projectile is anything that's going to be thrown or launched into the air. So it could be something like a rock that you throw, it could be a football, it could be a soccer ball that gets kicked into the air, it could be a cannonball that's launched out of a cannon. It could be something as simple as a rubber band that you are trying to launch into the air and try to hit somebody across the room with it. So any of those things would be considered projectiles because you give them some sort of an initial force and initial velocity, and then after that, once they are in the air, the only thing that affects them is gravity, because there's not any other kind of force or any kind of push or pull that's being exerted on there. Nothing's going to make them speed up or slow down with the exception of gravity. So all of those types of things are considered projectiles. So the path of a projectile, and what I have diagrammed here is similar to what was in your book. I used a cannonball as an example that's just been launched out of a cannon. And so let's say that we're launching this cannonball with an initial velocity that has an angle going up this direction. Now you guys have all kicked balls and thrown rocks and launched rubber bands and done this kind of stuff enough to know that this is the type of path that we see when we do it on the earth. And of course that's where we're all doing this kind of action anyway. I don't think most of us have been anyplace else, at least not very far from the surface of the earth, we'll put it that way. Okay, so the path that we're seeing is a piece of a parabola. Now, why is it a parabola? Well, the reason I can tell that it's a parabola is by examining the x and the y components of the direction. Again, remember that once this cannonball gets launched, the only thing that's acting on this cannonball now is gravity. And so there's no kind of push or pull or acceleration at all in the x direction. And so that means that as this is moving, the x component of the direction, no matter where I am in the cannonball's path, the x component of this is going to be the same. So I've drawn my arrows all the same length to demonstrate that x component. The y component, however, is different. The y component is, again, the x and the y components are independent of each other. And so the x component, since the acceleration is 0 in that direction, the velocity in that direction is going to be constant, okay? So I can analyze the x component just like I would any straight line motion that you've learned how to analyze back when we did that in modules 1 and 2. So if it's straight line motion in the x component, and you can analyze it that way. Now the y component, as I said, is different because the y component is starting out upward, but it has an acceleration due to gravity. So it's constantly being pulled downward. So the further it goes up, because acceleration is down, this component is going to become less and less and less until when it gets to its maximum height. At its maximum height, it's no longer going upward. It no longer has any velocity in the y direction. So at its maximum height, the velocity in the y direction is 0. And I just realized I forgot my negative sign on this acceleration here. The y component has an acceleration of negative 9.8 meters per second squared. Gravity is constantly pulling on it. At the maximum height, the y component is 0. There's still a y component, it's just 0. Then, as this cannonball starts to fall back down towards the earth, because it's being accelerated in the negative direction, the y component gradually gets more and more negative as it starts to fall back down. So what that means is that the velocity in the y direction is greatest at its launch. Here it's getting smaller, here it's 0, here it's negative, here it's even more negative, okay? So, because the only thing acting on it is gravity, I can analyze the y component just like I analyze any object that's in free fall. So if I just would have taken it and thrown it straight up and it falls straight back down, I can analyze the y component just like we learned how to do that back in, I think it was module 2. Okay, so the y component's greatest at the launch. At its maximum height, the y component is 0, and I can analyze that whole component just like an object in free fall, because that's really what it is. Once it's launched, it's really in free fall. It's just that it also has some motion in the horizontal direction as well. Now, if, and this is a big if the projectile lands at the same height from which it was launched, so what that means is that if this is sitting on the ground and it gets launched way up in the air, whiteboard's not high enough for that. So it gets launched way up in the air and it lands basically pretty much on the ground, then this statement will apply, okay? If you take the rubber band and you launch it from about where your face is and you hit your friend in the head, approximately the same height, okay? So if the projectile lands at the same height from which it was launched, the time to reach the maximum height is half the total time in the air. And we talked about this before when we talked about free fall, because we said the acceleration here is going to be constantly causing the velocity to go down. And because the acceleration is constant, it's at the same rate, the velocity is going to change at the same rate in the second half of the path as well. So if this starts out with a y component of, I don't know, let's say 30 meters per second upwards, then over here, this velocity is going to be 30 meters per second downwards. So the speed, assuming that the elevation is the same at both launch and landing, the speed is the same on both ends of this, just because the acceleration due to gravity is constant. Now, if the acceleration due to gravity was changing all the time, then that wouldn't be true. But because acceleration due to gravity is constant, speed at launch is going to be the same as the speed. Notice I said speed, not velocity. Speed at launch is going to be the same speed as it is when it lands, assuming the elevation is the same. Okay? This would be the halfway point if they land at the same height. So halfway point not only in horizontal distance, but also halfway point in time. Okay? So those are some principles that you need to keep in mind as we start analyzing things that are in projectile motion. So we're going to look at example 4.3, which is where we have one football player throwing a football to a second football player. He's downfield, the second football player is, and the first thing they ask you to do is to draw the path of the ball as it leaves the quarterback's hands and travels to the receiver's hands. Okay, so if it's thrown at an angle of 45 degrees, then it's going to go up at 45 degrees and it's going to have a parabolic shape until it comes back down. And that picture's there in your book and you can see that. So we want to know what maximum height this football is going to reach. So we're going to make a little space over here so that we can work this problem out. All right, so I know that my initial velocity is, was it 15? Yeah, 15 meters per second at 45 degrees from the horizontal, okay? So that's my vertical component, and this had a 0.0 on it, so make sure I got all my significant figures in there. And I'm looking for the maximum height. Now, if I'm looking for maximum height, that means I'm using the vertical component, okay? Remember, horizontal and vertical components don't affect one another as in any way. They're independent. And so I'm looking only at the vertical component. So the vertical component of my velocity in the y direction, so the initial velocity in the y direction, that's how I symbolize that, is going to be 15.0 meters per second times the sine of 45 degrees, okay? Because you'll have to remember that equation from when we did it before. So that should give me 10.6 meters per second in the y direction, okay? Well, what else do I know in the y direction? Well, I know that acceleration is a negative 9.8 meters per second squared. And notice this is negative. The football, when it's thrown, is going upwards. So this is positive. So things are all making sense here so far. Okay. What do I know about the velocity in the y direction when it hits its maximum height, well, we talked about that over here. We said at its maximum height, I'm treating this just like any object in free fall. Once it gets to its maximum height, the velocity is going to be 0. What am I looking for? I'm looking for delta x. I want to know how high this football went. Well, if I know the initial velocity, the acceleration, the final velocity, it's not too hard to find delta x, because I know that v squared equals v sub 0 squared plus 2a delta x, and then I can plug these things in and find it. So my final velocity is 0. My initial velocity is 10.6 meters per second, quantity squared, plus 2 times negative 9.8 meters per second squared times delta x. And then when you solve this, you're going to take this, you're going to square it, you're going to move it to the other side, at which point it becomes negative. Then you're going to have a negative here and a negative here, and those negatives will cancel out and give me a positive delta x, which is what I want, because I'm looking for the height that it rose from where it was launched, because I'm looking for maximum height. Okay, so when I do that and you crunch all this math, you should end up with an answer of 5.7 meters for the maximum height that it goes, and that's the height from which he threw it. So it's going to go, if he lets go of it from here, it's going to be 5.7 meters higher from the spot from which he threw it. Okay. Then the second part of the question asks us, in the situation depicted above, how long will it take the ball to reach the receiver who is 23 meters down the field? Okay, so if it's going to go 23 meters down the field, I'm now talking about the horizontal component of this velocity. So I'm going to get rid of this so we have some more space. So now if I'm looking for the horizontal component of the velocity, I'm going to change that. So I have the initial velocity in the x direction, and the initial velocity in the x direction, I don't use the sign, but rather I use the cosine. And because I'm using a 45-degree angle, this turns out to be the same. So it's still going to be 10.6 meters per second. Again, it's only the same because this was a 45-degree angle. Sine and cosine of a 45-degree angle are equal to one another. Okay, so now I still am going to use the equation, or I'm going to use the equation rather, delta x equals v sub 0 t plus 1/2 at squared. But remember, I don't have any acceleration in the horizontal direction, so this piece actually drops out because acceleration will be 0. I know that he is 23 meters down the field. So the 23 meters is going to go here. The initial velocity is 10.6 meters per second. And it's going to be a pretty simple matter at that point to solve for t. And t ends up to be 2.2 seconds down the field. Okay? If it took 2.2 seconds to go from the thrower to the receiver, at what time did it reach its maximum height? Okay, think about that for a second. It took 2.2 seconds to get all the way down the field. At what time did it reach its maximum height, which we calculated just a second ago? Well, we said if the projectile lands at the same height from which it was launched, the time to reach its maximum height is half the total time in the air. Well, if this is the time at which the receiver caught it, then the time that it reached its highest point would have been half of this, or 1.1 seconds. We're going to make the assumption that he caught it at the same height that it was thrown, just so we can actually work that problem, okay? So you can see that the problems that we worked here are not any different than the types of problems that we worked when we were talking about straight horizontal motion, when we were calculating the time it took it to go down the field. The time that it took to rise to its maximum height was just a free fall problem, which we've already worked before there too. The difference is that we had to make sure that we were using the component of the velocity in either the x or the y direction. So that's the piece that you're going to have to watch out for as you're working these problems.